Our next speaker is Marina Martinić Kavur, and she's a scientist who's now working at Genus, who co-developed the first commercial biological age test based on IgG and glycan clock, which you probably better know as glycan age. And Marina, take it away.
Hi, so I know this is going a bit off the topic, but life is unpredictable sometimes. Planes get canceled, planes get delayed. However, aging is not as unpredictable as planes. And I hope to persuade you, and I hope to today persuade you in this thesis and show the work that we've done over the last couple of years. So, glycan clock and glycan age. First question that I need to answer is why glycans? What are glycans and why? We haven't actually started in this field through wanting to develop an aging clock. What we are is we're experts in the field of glycobiology. And over the last, now we've celebrated very recently 15 years, we have actually published over 159,000 out of total of 191,000 published glycans. So we're actually leaders in the field here. And discovering an aging clock, which is based on glycans, was kind of accidental discovery throughout this process. But why it makes sense and why glycans make sense in this context? So first of all, what are glycans? Glycans are complex carbohydrates, and they're found on all of your cells, basically, and on most of your molecules within the body. It is just that they're not advertised as much as, other basic molecules of life. And what is very important, for instance, glycoproteins, when we talk about glycoproteins, glycans are nothing more than basically a secondary modification on top of these proteins, and they change the protein function as well as structure. But unlike proteins, which have a very clear template coming from the DNA, we don't actually have a single template for glycans. They're usually regulated by many genes, also influenced by environment, by what we eat, and so on. So already by summarizing, these basic facts about glycans, you start getting an idea why they would actually change with the age. And what the protein that is basically, our bread and butter is IgG. And IgG is actually a glycoprotein. So it's the most prevalent antibody in human blood. And it is glycosylated. It can be glycosylated on multiple sites in this upper variable region as well. But this depends on a somatic hypermutation. So some antibodies will have it, some will not. However, this glycosylation site here on the constant region is present basically on every single IgG molecule. And what it does is actually, so when glycans attach to this site, you can see they're placed in this middle cavity in the IgG, and they're effectively changing the shape of this belly. And why is this important? Because here and here, so at the edges of this belly of IgG, are the sites where IgG is binding to other cells and molecules of the immune system. So you can imagine that by simply, changing a little bit of this glycan structure within this central cavity, you can simply change the structure of IgG and thereby change an entire molecular pathway that this IgG molecule is later on going to interact with. And what we saw already in 2014, so this is published in 2014, but interestingly, the preprint of this paper was published on the very same day that, like the Horvath clock of epigenetic aging, so already in 2013. And we saw that the IgG and glycans change with age. So we noticed two general groups of glycans. First, we call them the pro-inflammatory in general group, which is basically increasing in the ratio throughout the aging process. So as we age, we have more and more of these glycans on our IgG molecules. And the second group is the anti-inflammatory glycans, or the glycans which are decreasing with age. So we start off having a lot of them, and then as we're aging, they're getting less and less. Now, what is interesting is that these changes of IgG and glycan actually resemble changes that we see in many, many diseases. So as I said before, we did a large body of the analysis of N-glycan throughout the world. We have thousands of, hundreds of thousands of processed samples. And what we saw is that these very, very similar changes occur not only throughout the aging, but in many, many different age-related diseases. And this includes cardiometabolic diseases, this includes some autoimmune diseases, this includes a vast array of different diseases. And we believe this is happening because IgG glycans are actually functional effectors that regulate inflammation. And I'm going to show you a little bit of the data why we believe so. But when we basically looked at this aging clock, so this was actually not published by us, this was published by a different group, but what they did is they compared glycan clock, so this IgG glycan clock, with other omics clocks, and this included metabolomics, this included also epigenetic age tests, and what they saw is that actually glycan clock is best at predicting future hospitalizations, and this was specifically linked to the future hospitalization that are connected to the age-related diseases. So basically, it was a good measure of a health span. And it was not only that we saw it, in general for some age-related conditions, we were also able to pinpoint some of the potential biomarkers for specific diseases such as future cardiovascular events. And this is something that we're actually now patenting in US as a biomarker of future cardiovascular events. So what we saw is in a very large cohort of thousands of women and men that the one single glycan structure on top of the immunoglobulin G was as predictive as American Heart Association score of the future cardiovascular events in women. And this was one single glycan structure. Interestingly, this was true for women. For men, we were also able to predict it, but not with only this glycan structure. It was a little bit more complicated. Potentially, this is because women and men age differently, and we believe there might be also some of the influence of menopause here. I'm going to show some of the menopause data later on. But here, in this case of cardiovascular diseases, we were also interested to find out what is actually going on from the functional side. Why is this happening? Can we figure out a mechanism? So we did a collaboration with a group who is working in mice, because we can't do this in humans, of course. And what they did is they bred basically obese mice. They fed them with a high-fat diet, which effectively raised their blood pressure. And what they saw is that the group which had a higher blood pressure had more of these pro-inflammatory glycans. So these are these shorter glycan forms that don't have the sialic acid extension. So in general, if you think about pro-inflammatory glycans, they're shorter. The more anti-inflammatory ones are longer. And this was the case for these mice. So mice which had higher blood pressure actually had more of these pro-inflammatory glycans. Now, the interesting thing, when these authors actually took the IgG from the mice with a high blood pressure, so this pro-inflammatory IgG, and they put it in the peritoneum of the B- mice. So these are mice which don't have their own IgG. The effect was that basically B- mice then also had a high blood pressure. So just adding this IgG with pro-inflammatory glycans was enough to cause a high blood pressure in B- mice. Furthermore, when they fed the obese mice with a precursor of this sialic acid, so it's called manosamine manac, let's call it sialic acid precursor. So when they did this, what they saw is that just adding this supplement to the diet of the mice effectively lowered their blood pressure. They were still obese, but they did not have high blood pressure anymore. So simply supplementing with a precursor of sialic acid was enough to, disconnect the link between obesity and hypertension. Now, what we believe how we could use this knowledge and build upon it is that we would like to develop biomarkers and predictors that could help us change the course of the diseases and change the course of aging in such a way that we're never crossing this point of no return, but that we start with the interventions before the disease actually occurs. And why we believe it is possible to do so is because we can actually see the changes in glycans in humans even up to 10 years before the symptoms of the disease. Now, in humans, it's not as simple as it is in mice. You cannot just supplement them with a precursor and cure a disease, so there might be some influence of the genetic background. There is still a lot that we don't understand, but what we want to build upon and what we really do want to develop is early biomarkers for these diseases and for aging and to detect a problem before it occurred. You can compare it to changing your tires. So you basically change your tires every year. You don't wait for your tires to explode on the highway to change them. Whereas our entire Western medicine is based on, treating exploded tires, which is completely crazy if you think about it. So what we do really want to do, and what is the title of this talk, is to now turn back this glycan clock, to return it and to decrease the chance of developing these diseases. And one of the things which we saw works was caloric restriction. So this was a meta-analysis. This was a huge study, over 700 individuals on a low-calorie diet. So this was done across 8 European states. And they were on a diet for 8 weeks. And basically, people who had 8% or more of the weight reduction after 8 weeks, one important thing, they started off obese. So most of these people had a waist circumference of over 100 centimeters, and their BMI was very high. And basically, after 8 weeks, we could see significant changes in the glycans. Now, it did differ between some medical centers, potentially also because different European countries have different cultures, different food, and so on. But in general, we again saw this trend of decreasing the pro-inflammatory glycans and increasing of the anti-inflammatory glycans upon this weight reduction and after caloric restriction. We saw also in another study, so this was a study where we looked at 37 individuals that underwent bariatric surgery. And they were classified to be good candidates for bariatric surgery by NIH, so they were also very obese individuals. And what we saw is that even after the first short period, this was only 3 weeks of low-calorie diet, we already saw some improvement of the profile of glycans. However, after 6 months and 1 year after the bariatric surgery, so basically when they experienced an extensive weight loss as a consequence of bariatric surgery, there was a drastic improvement in the anti-inflammatory glycans, specifically glycans with 2-galactoses, and a decrease in the pro-inflammatory glycans, the glycans without galactose. Another thing which is well known as a lifestyle intervention that could work to basically decrease the risk of the diseases is exercise. And in this study, we followed around 30 young men, otherwise fit men, and it's important to mention this. There are other cases which we could discuss later on in the questions if you want, where this is not working. But basically in this young, healthy, and otherwise fit individuals, intense exercise was by itself with a decent recovery period of around 6 weeks of exercise and 4 weeks of recovery was enough to change the profile of IgG glycosylation. Another interesting thing, potential intervention that we're exploring is, of course, the change in the microbiome. So we did one study with fecal microbiota transplantation. We did not see, after this period, significant changes on the IgG glycans themselves, but we did see a very significant change in the plasma glycome, which includes also other glycans within the blood on other molecules, not only IgG. And we're actually now developing another clock, a metabolic clock, for which we have significant amount of data that it correlates to some other things, for instance, like diabetes and metabolic health. And one more intervention that we're intensively working on, and for which we believe it has a huge potential, is HRT. And I was actually interested in this when we talked about dogs, because dogs don't actually experience menopause, if I'm right. But in women, in humans, we do have this phenomenon of menopause, which is not even happening that late. For vast majority of women, this is happening in late 40s or early 50s. And menopause causes a huge shift of IgG glycosylation between this young to old profile. And this is really something that we started noticing when the clients were coming in, that they were having a very, very good glycan profile, and then all of a sudden a huge shift would occur within a time span of 6 months. And when we looked further into this, it was the menopause which was the driver between this huge shift. And we went further into exploring this and what is actually the causation, between this shift in the menopause. And we saw that suppression of gonadal hormones in a placebo-controlled randomized trial actually identified a strong effects of estradiol. So basically in this group, the red group here, these were women in which there was only a suppression of gonadal hormones and supplementation with placebo, but this blue group received estradiol. So this was artificial menopause in the red group and supplementation in artificial supplementation in the blue group. And you can see that the red group actually experiences about 25% increase in biological age, whereas the blue group did not experience it. Now, after we stopped the suppression of gonadal hormones, the red group returned almost to the baseline. And this was a nice experiment showing that it is actually an effect of sex hormones, or in this case specifically estradiol. So we wanted to explore this further, and I'm showing here for the first time the results of a small study which we did in UK. So this was done on 42 women which entered menopause between the ages of 40 and 60. And we wanted to look from before the point when they started doing the HRT and then follow them up for the next 3 and 6 months. And what we saw is that all of the women that entered the HRT treatment, so this was with bioidentical hormones, and this was primarily transdermal therapy, actually experienced a change in their biological age. Now I'm saying a change. For the vast majority of women, so 38 out of 42, so 40 out of 42, we saw a drastic decrease of the biological age. For 2 individuals, we actually saw a drastic increase of biological age, and this was a huge increase. This was an increase of like 16 or 20 years. Now, what we're extremely interested in now to follow up is, are we actually in this group, detecting possible ways to use this biomarker in the optimization of HRT therapy? And we're exploring this further to see if we can actually optimize both the dose or potential side effects of the HRT through using this as a biomarker. And this is something that we're now exploring further. And of course, the last question is, how much can we actually turn this biological age clock? And we don't have the exact answer to this just yet. But we did do some models. We based it on the data that we already have and on the large twins study, which followed women for over 20 years. And our best models and best estimates say that most likely around 20% of what we see in the biological age, in the glycan biological age, is the effect of lifestyle. So this is something that most likely we can change through simple lifestyle changes. The rest of it is something that is both genetically predisposed, around 40% is an estimate of how much is genetically predisposed. And then another 40% is something that we called chronological age. But in effect, this is something that we're sharing in the environment where we live. So this could be epigenetics. So the epigenetics of the aging, this could be some shared environmental traits. We don't know exactly what is behind it. And with this, I'm finishing up my presentation. So thank you all for the attention. I will take any questions.
Thanks. Have you looked at the relationship in the obese subjects, but are you seeing a change in neuraminidase? Are you seeing a change in sialotransferase?
So in these longitudinal studies, we did not look at these other parameters. We do have, but this is not a longitudinal data. This is the initial data on which we base developing a biomarker, where we do see a correlation with BMI, with C-reactive protein, with other factors of inflammation, for instance, with triglycerides, LDL, and so on. But we are, of course, interested in following up more, of the other measures and other markers and comparisons to see how they are changing in comparison to the IgG glycans.
But you don't know if there's a change in the metabolism independent of that for precursors, or if there's an enzymatic change?
We cannot give an exact answer to this, no. I mean, speculatively, most likely, but I do not have the data to support this.
I was fascinated by the fact you measured estradiol drops with glycan age, but when the average woman stops menstruating, her estradiol is only down about 50% from her youthful level. Her progesterone's down about 75%, and her testosterone's down about 80%. And it's probably the drop in progesterone that causes her to stop cycling, because she still has plenty of estrogen on board. Have you looked at the other two primary sex hormones and their effect?
We're looking at it now. So we're doing this study now. We have this preliminary data. We're actually expanding this in a bigger study, and we want to look at both the effects of estrogen, progesterones, testosterone too. We do have some observational data, for instance, from the clinics with whom we're collaborating with, that when they treat their patients with testosterone, they also see an improvement. However, if they use, aromatase inhibitors, if they stop the conversion of the testosterone into estradiol, then basically they don't see a positive effect.
And that makes good sense, as the average 20-year-old has about 3 times more testosterone than estradiol in her system. And so, all right, thank you.